tolerancing, what is it? The author kind of tells you in the first paragraph of section 8.4, and I kind of summarized it here on my notes if you want to know what this is. So tolerancing. It is an allowed variation of a part from its basic dimension. The allowed variation of a part from its basic dimension. Another definition they use is the amount of slop allowed in the manufacturing process. Kind of both say the same thing, slop.
Like slope kind of, but slop.
Slop.
Nope, like junk.
Like slop means we know we aren't building it to exact size, so how much room are we going to give them to make errors? Okay. Slop might be construed as error in this situation. I've also got up here, or the difference between the upper and lower limits. That's what kind of subjective depending on how you dimension the object, and we will see that. Keep in mind, when we tolerance, almost always when you tolerance, it will be because the part you are making mates with another part. Okay, that's in essence why we use tolerancing. Now, right now you're doing a general tolerance where you say all dimensions plus or minus 0.02 inches in your general notes, which applies to the drawing as a whole, or all dimensions plus or minus 1 millimeter. Again, those are applying to every object on there, and we don't really know if our parts are mating with other parts. We're doing them as standalone. Okay. So we're kind of driving the workforce on that. But in essence, really tolerancing is all about how a part performs with the parts that are mating with it. That's what it's really meant for. We've heard the term standardized parts, interchangeable parts. Your author makes a big point of this, and the paragraph on page 843 in the top left, where he's talking about the interchangeability of parts. And this is really, we've mentioned this many times in here before, this has really revolutionized how we do things. I mean, if you think about it, go look at the automotive program, or auto body, or even the welding program. How much real fabrication really goes on in our world anymore? In essence, not near what it was 100 years ago. Now what we do is we do parts to a certain tolerance. When a part breaks, we take it out. We don't fix it because it costs too much. We throw it away and we put a new part in there because it's the most efficient way to get things done. In essence, that's what's driving it. We do have some other reasons for tolerancing. I put them right here, just a few of them. This is not an all-inclusive list by any stretch of the imagination, but the performance of the parts. What does tolerancing do to the performance of a part? Any thoughts on that? So if I have two mating parts that are working together. Yes, Devin?
You can make it more efficient, get more out of it. If you know
Okay.
exactly what.
Make them last longer?
Yeah.
Okay. Now, when we think about that, when I want to make a part last longer, would my tolerances be smaller or would they be larger? Generally, the smaller the tolerance, now this is not all-inclusive either,
Yeah.
but generally, the smaller the tolerance, the longer the part will last. Why? Because it has less friction, right? It's not banging as parts move, so therefore you reduce wear and tear. So generally, if you have a tight tolerance, a part will last much longer. Believe it or not, we do build a lot of parts with very sloppy tolerances specifically so that they will break. And there's two reasons companies do that. Number one is they want the part to wear out because it's a cheap part and it's protecting an expensive part. And then two, and you may think this is not morally or ethically correct, but it happens and it's out there, is that they want the part to wear out so that you have to buy another one. And do you think that happens out there? You bet it does. That's just good business sense, especially when you have a monopoly on a market or something. Now, I don't know if everybody's got to weigh that in their own mind, but it's out there and it happens. So you've got that going on. Safety, always a biggie. Okay? If we have things moving and operating under a lot of pressure, we want those tolerances tight, so if things break, we don't injure people. And we need to contain those breaks and how they work. I think Angie mentioned that she was specifically doing safety on these conveyors. And there's a lot of safety on there. Most of it's controlled by electricity. But you certainly have your old standbys, which are your guards, and all of these items too. And they have to be toleranced out. We already talked about that. Okay, so keep in mind, this is always pretty much some of the major categories of why we do this, the tolerancing. Now, let's look at how we go ahead and apply these to a part or a feature. First off, you can do direct tolerancing. Now, when I say direct tolerancing, as opposed to general tolerancing, I'm not really going to go into the general. You know what the general is. You're doing it right now. In the general notes, we put a tolerance, and that applies to every dimension on the object. Therefore, we don't put a tolerance with your dimensions. Your dimension of width is 6, and you're saying it's 6. Now, you know if you're doing that to English units in here, the part will be plus or minus 0.02 inches off of that dimension, and that's a general tolerance. Applies to everything on the drawing. When you start getting mating parts, we move to a direct tolerancing item. And by this we mean applying the tolerance to the dimension in question. Now they give an example right here. These are our 2 ways that we apply a direct tolerance. This one's called limit dimensioning. Okay. Notice here there is no one size. We give the upper limit and the lower limit. The upper limit is always on top, lower limit is on the bottom. In essence, they've got a zone they need to hit. This is a direct tolerance. You also see another direct tolerancing down here. This is called bilateral tolerancing, where we come in, we're saying the basic size, this is what I want. If I can, I want it at 4. But I know you can't get there, so I'm going to say plus or minus 0.003. Now, one thing I don't like about this example right here, the author kind of made a little bit of an error. Can anybody pick out what the error is on that? I put it on some of your drawings as I was correcting them the day before Thanksgiving.
Zeros after it's 4.
Significant figures don't match up. Okay? And this is bad dimensioning technique. This should be 4.000 if I'm going to take my tolerancing to a 10,000. Okay? So you want to make sure those kind of match up. But the point being on this drawing is that you can allow it to where it goes. Now, if you use a plus minus, they can go upper and lower. Tell them we want it at 4, but you can go 4.003, you can go 3.997. And anything in that zone is acceptable. So direct tolerancing, applying the tolerance to the dimension itself. Now, when we look at those, you've seen the limit. That's that one we just looked at right here, where you give the upper and lower limit. By the way, if I have an upper and lower and I'm using limit tolerancing like this one right here, what do you think the craftsman is going to try and build it at? Based on the numbers I give you here? Yeah, he's going to try for a 1, right? Because that's going to give him the maximum amount of error. Now, when you do lateral tolerancing, you have one that's called bilateral, where you give a basic size. Okay? By basic, if you remember right at the start of chapter 17, we looked at those basic dimensions. This means this is our theoretical perfect part. You give a basic size, and then you give the deviation. If the deviation is the same in both directions, you can use our plus minus. Now remember, these are going to mate with other parts, so sometimes we do not want these the same. Okay, so then you would go to a lateral tolerancing that changes. Okay, I just kind of wrote an example of one right here. Okay, where I would put my dimension, this is my basic size, and then I put the deviation from that with half of the size text, so this would be 16th text, and I put plus 0.01, so I'm allowing them 1/100th of deviation in the positive direction, but then I'm going to allow them 4/100ths in the negative direction. So we can mix that up. And in fact, you're going to find tomorrow when we do fits, this can actually be a basic size, and it can be plus here and plus here. Because we don't really want it 1, but it's maybe with a device that's set at 1. Okay. So we can do plus plus. We can do minus minus, where we don't want it at 1, we want it lower. Okay. So what you would then do is hand calculate your limits. So if I had a minus minus here, the craftsman is then going to build this at 0.99, 1.00, let's see, oh wait, doesn't go positive. Okay. It would be 99 to 98, 2.96. Those are the acceptable sizes. Do you see where I get those numbers? Okay. If I take my basic size,
Oh,
and then I apply my tolerance to it. So 1 minus 0.01, if this was a plus, I would add it. So minus 0.01, minus 0.02, minus 0.03, minus 0.04. Okay. So I can get that whole gap there.
Oh, okay.
Okay, so this is called lateral tolerance. Yes, Mike?
So in this case, they will not make it 1?
That is correct. Yeah. Seems kind of weird, huh? Why would we put the 1 there if we're not going to make it a 1? You'll find out we do have some standardized parts that are based off what we call a nominal size, and we'll define nominal here in a minute. And this would be a nominal size. This has got to be a main part that's driving this.
Can you, so that's lateral, can you go back to the bilateral? It's just,
The plus minus one?
that one's lateral, you said?
Yes.
This one's bilateral. So go
Yeah,
back.
it's actually, this would be considered lateral if I was doing minus minus because they're both going in the same direction. Bilateral just basically
Put
means
it all in one,
you're going up and down.
okay.
So with that one, it would also be like 0.99, 0.94, 0.95.
The acceptable
Or it would
sizes
be
for
like
this.
0.05.
Point 96, 0.95. Anywhere in that zone.
Yeah, that's it.
So of course, there's a 03, 02, 01, 0, 99, 97, and then the other ones I've got written here.
But they will first try to build it out one.
Yes. Mhm. That's correct. You're going to find when you do this, this is really where you get into the fine details on how you're going to construct something, okay, and how it is going to perform through the life of the part. You really think about that. In essence, you're getting into the manufacturing process here. All right, any questions about direct tolerancing? Direct means you're using limit dimensioning, such as this one, or you're using bilateral, like these two. Now, nominal, we got a bunch of definitions, and these kind of pop up starting on page 845, and let's go ahead and look at those. So what does nominal mean? You can read it right out of the text on page 845. A dimension used to describe the general size usually expressed in common fractions. Folks, a nominal size will be dictated by your workforce. And it's usually done fractionally, even if we're using decimal dimensioning. Does anybody know what our nominal size is in here? Generally, what have I asked you to memorize as far as fractions and decimals? Every 16th? Okay, if I was working in this environment, we would probably use 16th as our nominal size. Now, if you go to a machine shop that has some resources, not a great, maybe you're going to a 32nd, and that is their nominal size. Usually we look at it as the base unit as a fraction. There are places that will work 1/128th, that's their nominal size. And 1/128th is pretty small. That's going out to, what, 3 decimal places? Okay, which is pretty tight machine shop to be able to do that. So it's dictated by where you go to work. Keep in mind that even when we use decimal dimensions, we consider that a fraction. So I just kind of put on here, as for us, like a 1/2 inch, that's considered a nominal size. A 16, 3/8, 5/16, 7/16, 9/16, 11, all these. When I come to something that's a little outside of it, I'm using a fraction that's maybe a little different, like 0.42, 0.473, something that doesn't line up with my nominal sizes. Again, dictated by where you work, in essence, it's your rounding. You're going to round to a nominal size. That's what we do. All right, the next one, basic size, theoretical perfect size. It's used for the start. Right? We tell somebody, hey, this is what I wanted, allow you some deviation, where's it at? So that's the basic size. You've already heard that. Let's see. One you haven't heard, allowance. What is allowance? Allowance specifically goes with mating parts, like these two devices right here. Now, I don't know if these two were originally made, but they fit pretty close, so we'll say that these two were designed with each other. Allowance happens when these two parts are constructed at maximum material condition. In essence, it's the tightest fit that can occur between mating parts. Okay, so allowance. The amount of slop that occurs at maximum material condition. Or the tightest fit you'll have. That's allowance. Very useful term. Because if I'm trying to join these two parts together, what's the first thing I'm probably looking at?
If it fits.
Yeah, is how it's going to fit, right? Because if I build this such that it will always fit into here no matter what they're built at, I do not need any hydraulic presses. I don't need anything. I can just hand them to two people and they slide them on and bolt it together. Many times we might build this to where it never fits in this and it's a joining method. I have to use presses, so I would take this and shove it in there with some machine so that it removes material from both of them. Now it's joined on. Now, those of you that have worked on your cars and you see bearings that you have to use pullers on, that's how they're constructed. Holds them together. We can have a lot of different methods, but that's how we join them. We always look at allowance. That's the first thing we look at. But that's one term. Now, when I said allowance, the tightest fit or the condition at maximum material condition, we already talked about what MMC or maximum material condition is, but I'll refresh your memory. What is MMC? It is the size of the part when it has the most mass. The size of the part when it has the most mass. Yes, Sharon?
Going back to the allowance, if you have a part that has to be shoved on by a machine, is there an overlapping allowance, and how does the allowance work on those?
Same. The allowance works the same. Okay. But what you would see, if your allowance is ever a negative number, and you'll see this tomorrow, we're going to look at this. We call those our fits. When it's a negative number, they don't fit, and I need a mechanical device to put them together. If it's a positive number, they always fit together, and I can just slide them on and off. Okay? I don't need a machine to help me, or a big hammer, whatever you want to think of on that. Okay? We're going to actually work with some allowances tomorrow. I got a worksheet I'm going to give you out so you see that, based on how objects interact. Okay, let's talk a little bit about MMC. I'm going to look at 2 items. Okay, and I've given some tolerances for it. So we're going to take and compare 2 items that mate together. So we have a shaft. Think of it like this guy. Okay. We want it 1. We'll allow them 200ths in either direction. Okay, so we're going to use bilateral tolerancing. We've got a hole, this inside collar right here. Okay, that's going to mate with this. We've given it a dimension, 1, using bilateral dimensioning, but it's a little bit different. Okay, right? This one will go 400ths in the positive, 300ths in the negative. So when are these guys at maximum material condition? Well, that's how it's going to fit. So we want to look at these and look at the tolerancing that's involved. I wrote a little chart out, and I'll put this up on my notes. Okay. So based on those dimensions I just gave you, and let me kind of do both these sheets at once. By the way, isn't that a nice, great line quality drafted drawing?
Yeah.
Looks like my doctor's sketches. So the hole sizes. What are the sizes that we can get? Highest size, 1.04. Lowest size, 0.97. Okay, do you see where I get that on the hole sizes?
Yes.
The shaft sizes, what can they be? 1.02 down to 0.98. Do you see where I get those sizes? Now, the thing we want to look at when we look at this is my tolerancing range, or the amount of slop I'm allowing. What is maximum material condition for this hole? When does the hole have the most mass?
When they're both at 1.
0.97. That's what's math.
When does the hole, this thing, have most mass?
0.97.
Okay, Lisa, you're saying 0.97. How many agree with Lisa?
When the hole has mass,
When the hole has the most mass.
then I agree with Lisa, yeah.
It's when it's its smallest, right? Because it's a negative cylinder. The larger it gets, the less mass the part has, right? So the hole is a maximum material condition at this point. Okay, so this 0.97 is MMC. We have another term out there called LMC, which stands for least material condition.
So that would be the highest.
Yes. Now, on the shaft, when does the shaft, this guy, have the most mass?
Oh, 1.02.
The most?
1.02.
Yep.
0.8, 0.8.
When the shaft is the biggest, it has more mass, right? This is LMC. Now, why are these terms important? If I'm engineering these parts, does it make sense that I look at them at LMC and then I look at them at MMC? Does it make sense that everything, if those work at those 2 conditions, does it make sense everything in between works? Can I make that assumption? In theory. We don't. We test it at all parts, especially if safety is a consideration, because things do break down occasionally in the middle. But this is the place we start. And we make on the original assumption that if it works at MMC and it works at LMC, it will work in the middle. Now, certainly we go through prototyping and these types of things to test that theory.
It doesn't make sense the biggest shaft to go into the smallest hole. That doesn't make sense, actually.
That's actually your allowance.
Okay.
Now, how are these 2 parts going to fit together? Look at them at maximum material condition. So if I take the hole at 0.97, and then I subtract the shaft at 1.02. So I just look at that, so I'm going to look at my allowance. Remember, allowance is when the parts are at MMC. Okay. So I take my hole, it is 0.97, and I'm gonna subtract my shaft, which is 1.02. What is that equal to? A negative 0.05. Did I do my math correct?
Yeah.
Since it's a negative number, these two, if they are built at maximum material condition, they're gonna have 5/100ths of interference when I put them together. Okay, 5/100ths is pretty small, right? A 16th is 6/100ths. So we're a little bit less than a 16th. Well, if I'm dealing with steel, can any of you strong enough to take tube steel parts and push them together and remove that steel? No, none of us are. We'd need a very big hammer to get those together. Now, if I'm doing something like plastic, yeah, maybe then I can do that. But certainly we probably would still use a machine. But it's telling you right here that these will not fit together. When I join them, material's got to be removed from one of the two of them, or both of them, to make them fit. Now, if you look at them at least material condition, because technically, statistically, I can have parts made at this, I can have parts made at that, but I can have them at any size in this zone. I look at least material condition. They don't have a term for this one. You just look at the other limit. Okay, so this would be at LMC, it is 1.04 minus 0.98. Well, what's that equal to? A plus 0.06 if I did my math correct. Okay. So this can happen too. And the parts are still acceptable. Here, I don't need a machine to help me join these. But what it does tell me is I've got some slop here. These things are banging a little bit, right? You've got a 1/16 of air in there. So if this shaft and this wheel is turning at 6,000 revolutions per minute, I'm going to get some wear.